Hello and welcome to a previously recorded version of TA Instruments QuickStart training class for the SDT Q600. My name is Louis Wagensback and I'll be the instructor for this course. First off, I want to thank you for being a customer. The fact that you're taking this class means that at some point in time, either you or someone else at your company purchased equipment from us, and we appreciate that. This is one of a series of courses designed to ensure that you get the maximum benefit out of your thermal analysis instrumentation. Now, this is a pre-recorded course, so if you hear the audio for this course, you must have a sound card with speakers installed. There's also another couple things that are different about this pre-recorded course. You can't ask questions as we go through, obviously, because there's not an instructor live here. But what you can do is you can write down the slide number and email us questions. And there'll be an address at the end of the presentation that you can email that to. Now, the slide number's in the lower right-hand corner, and you will see here it's under this TA, and it's right there. This is slide number 2. So that is the slide number, and it'll be on each slide as we go through. One other thing, there is a bar that is a WebEx player controls, and you can move that around to get it out of the way, but that gives you the control to pause a presentation, to back up the presentation, or to fast forward the presentation. Okay? So that's it. Let's get started now. This is the agenda. We're going to go through a basic introduction, just some basics on the SDT. Then we're going to talk about how to run a typical sample. So we're going to go through and using the Terminal Wizard, we're going to set up the sample, the instrument, program it, run the data, collect the data, and analyze the data. And then we're going to go through some other topics like calibration, etc. Now, a couple basic things. What do we want you to learn out of this course? After completing this course, you should have a basic understanding of the SDT, the ability to set up and run a typical experiment using the wizard, and an understanding of other issues such as calibration, sample preparation, etc. Now, what is an SDT? SDT stands for Simultaneous Differential Technique. And what the SDT is it's a DSC and a TGA, both at the same time. So with the DSC, we can measure heat flow. With the TGA, we can measure weight change. And so we can measure both these at once, one instrument, one sample, ran at the same time. So probably the most common for this is things like inorganics, high temperature materials, because the SDT will go up to 1500 degrees C. But it could also be used to analyze normal polymers, pharmaceuticals, etc. Basically anything that you want to measure heat flow and temperature both at the same time. Now let's go through how we're going to go through and run a typical sample. Here are the steps we're going to do. We're going to prepare the instrument. We're going to prepare and load the sample. Then we're going to start the Thermal Advantage software. We're going to use the wizard to run an experiment. And if you haven't used the wizard yet, it'll go through and show you how to do that. It's a pretty handy tool. And then we're going to use universal analysis, we call it UA, to analyze the data. Preparing the instrument. There's a couple things that we need to talk about on the instrument, but this here is a picture of the SDT, and we can see the control screen that's highlighted here. So this is the touchpad, and if we kind of blow up that so we can see this is our main menu that we would see. We've got start and stop controls. We've got a reject here that's kind of grayed out, but that would be active if we're running a sample. Then we also have a button for the control menu and the display menu. If we hit that button for control menu, we'll see this screen. Now we still have the same across the bottom here, but what it gives us the controls for the furnace, the tearing. So the furnace will either open or close, depending on where it's at. It'll go the other direction. We could switch gas manually from here. We could turn air cool off and on from here. And then display menu will just show you the different signals, etc. Now, one of the things we need to make sure is that the purge gases are hooked up. If we look at the back of the SDT, we'll see a port for 3 gases to come in. One is the gas 1 purge, The second is gas 2 purge, and then we have for cooling gas. Now we're going to talk about cooling gas or cooling later, and we're also going to talk more about purge gas. But this is where they're hooked up. And notice here, 20 psi inlet max. That really should say 20 psi, because you really want that coming in there at 20 psi so the mass flow controller will control the flow properly. Now the cooling gas down here, that is 120 psi max, but it needs to be between 15 and 120 psi to get proper cooling. Okay? Now let's go through preparing and loading a sample. One of the first things we need to do is pick a sample pan to use and make sure it's clean. And we're going to talk about the different sample pans later, but right now I'm going to use a 90 microliter alumina sample pan or ceramic pan. Now here, one of the first things I'm doing is cleaning it. So I took this pan, I put it, held it with tweezers and put it in a Bunsen burner, or actually in this case it's a propane torch. But I'm burning off anything that's on that pan to make sure it's clean. Then I'm going to put the pan and the reference pan, and they both need to be clean. I'll put it on the beams, and I'm going to close the furnace and do a tare. So we get 0 to begin with. Then I'm going to get my sample. In this case, I'm going to run kaolin. And I'm going to load this in the sample pan. Now when I load the sample pan, I'm putting it here. This is the top of the balance assembly. There's a little tray that you could do it on. I did it here because the picture shows up a little bit better. But what you don't want to do is load the sample right here on the beams. And we will talk about that later also. And then lastly, you would load the pan onto the beams, close the furnace, and then you could start your program. Now we're going to go through the software. Normally, the Q-Series Explorer starts up when you first start up a run, or when you first start up your computer, excuse me. But if it's not, there's an icon on your desktop, and you can go to that and double-click on it. Now, when we open up the Q-Series Explorer, it shows all the instruments that are attached to the system. Now here we've got the Q600 highlighted that we want to open, but there's also other instruments like a TGA and a DSC and a DMA. So if we double-click on this Q600, it'll go in and open it. This is our basic view that we see when we first start off on the SDT. This is the experimental view, and the icon that's highlighted here is the icon for this view. Now these first 5 icons here are for controlling during a run. This is start and stop and reject and pause and resume. The next 3 are for controlling the view that we're looking at. This one is experimental view, and then there's 2 others that we'll look at shortly. And then there's other icons, the next one's for tear, etc. Okay? Now all these icons have flyover help. So if you hold the mouse over the icon when you're in the control software, it'll pop up the flyover help of what that is. Now let's look at the different screen here. So first off, let's look at the signal display. This gives us real-time the signals as we're running it. So you can see here we've got things like remaining runtime. Obviously we're not running at this point, but that's how much runtime we would have for the method that we've selected. The actual temperature is there. The actual weight in milligrams, and then the weight in percent, and then we also got heat flow. These are some of the signals that we would see there with the SDT. The box under that is for the method segment. Now, currently I've got set up where we're going to ramp 20 degrees a minute to 1300. And we're going to make a run in a few minutes, and as we're doing that, I'll tell you how you can modify a run during the process. But this box is where we do that also. The bottom right-hand corner is a real-time plot. This would show the data as we're running the sample. Right now we've got weight in milligrams versus temperature. So as we started heating up a sample, we would see the weight change. If it lost weight, which is most likely typical, or if it gained weight due to oxidation or something like that. The next center section is probably one of the most important, one you use a lot. It's the Summary, Procedure, and Notes page. And you can see across here we've got 3 tabs, Summary, Procedure, and Notes. Now later on we're going to go through and fill out this in a manual form by clicking on those and filling out each page. What we're going to do here in the next couple minutes is go through and fill these out using the wizard, but you'll see that it'll all be the same. We've also got things like what mode is it in, is it standard mode or calibration mode, what test are we running or template, and we'll talk about all this later. Now this icon right here to the right of mode is our signal selection icon. And if we click on that, it shows us what signals that we can store. Now these are all the signals that we can store in a SDT instrument or SDT experiment. Now normally what you would want to store is the first 4 and then the last one. So I would always store time and temperature, I would store weight, and I would store heat flow. Normally I would not store the temperature difference in either degree C or microvolts. That's kind of the raw data that you don't really care for. You're usually wanting to get out the heat flow data. But I would usually store the sample purge flow. That's an important thing to be able to go back and look at that in the data analysis to make sure that the purge gas was flowing like you expected it to and you wanted it to. So anyway, this is important to make sure you pick the right signals. If you're trying to run this and get a DSC data out of it, if that heat flow is not checked, you won't get DSC data. If all we had checked was time, temperature, and weight, then you would just get time, temperature, and weight, nothing else. So that's kind of important. Now the last one over here on the left is the sequence, and this just runs in a sequence. Now with the SDT, we do not have an autosampler, but you could still go and program multiple runs. So maybe we have 4 runs that we want to do today, and we can sit there and program all of them up, and then have the samples sitting there lined up. We run the first one, and then we would go to the second one, tear the pan, load the sample, run the second one, etc. I told you there was 2 other views. This is one of them here. This is the center one that's got it's highlighted here, this icon. This shows real-time plot here in the middle screen with our signals and our methods. So this is like during a run you would normally look at this maybe. And then the very last one on the far left, this icon that's over here that is now highlighted, is real-time plot full screen. So this will show you real-time plot as you're running, and it shows it full screen without the other information. If we go back to experimental view, we're going to go in and start the wizard to run an experiment now. So this is back in our experimental view, and we're going to start the experimental wizard. It's highlighted here. It's a little magician's hat and magic wand. So if we click on that, it's going to start up the wizard. The first thing it's going to do is ask us what type of run do we want to do. This is the template that we're going to use. And we'll see that when we fill this out manually later. So what we're going to do is an SDT temperature ramp. But you can see there's other experiments like a cyclic experiment, isothermal experiment, stepwise isothermal, etc. Now this little icon right here actually changes depending on whether it's a ramp or a cyclic. So in this case it's a ramp, so it's just showing that we're going to time and temperature, we're just going to increase. But if we were doing something like a cycle, it would go up, back down, and back up. So it would be a heat, cool, and a reheat. So that's basically what we're doing here, and that's what this icon shows. When we're done with this page, we make our choice, then we click Next. And we're going to go through this on all the different pages. I'm not going to keep telling you to click Next, but that's what happens. Pretty self-explanatory. The next screen is our experimental test parameters. So we're going to ask us for a start temperature and a final temperature, and also our heating rate. Now this box here that says use current means that wherever the SDT is, we're just going to start ramping, in this case at 20 degrees a minute until we get to 1300. So this could be at basically ambient, or it could be at 100 degrees, just depending on what temperature the furnace is. If you don't want to do that, if you want to start at a specific temperature, like say 50 or 35 or something, then you would uncheck that and then type it in here, and you can see it's grayed out. Now remember, this is on the SDT, there's no active cooling, so you can't try to start a run below ambient, and even trying to start at 25 would be a little difficult. Other choices we have here is switch gas. If you want to do an experiment where you switch gas at some point, you could check that. And when you do, this would pop up and allow you to type in which temperature you want to switch gas at. Or if you want to hold at a final temperature, you can check that, and then it would tell you how long you want to hold there at the final temperature. There's two other choices here for advanced parameters and post-test conditions. So if we click on advanced parameters, it gives us our data sampling interval. So this is where we put in how many data points we want to collect. And the default here is 1 second per data point, which is typically what I use on the SDT. We can say OK to that and click on post-test conditions, which gives us our method in conditions. Now, do you want to leave the furnace closed at the end of the run, or do you want to open it at the end of the run? This is what it's asking. And do you want to air cool? The choices that I've got here are how I typically run it. I leave it closed at the end of the run, and I turn on air cool to maybe somewhere around 50 degrees. Now, what happens with the SDT, at the end of the run here, it's going to leave it closed, and there's a fan inside. The fan's going to turn on immediately and start cooling it down. When it gets down to around 600 degrees, then the air cool will turn on. So you'll hear a pop where the solenoid valve opens and it blows air through it. And if you was supposed to open, it would open the furnace up at that point. The reason I leave it closed is twofold. One is this protects the beams, because those beams are there. You don't want to get your lab coat or something falling and hitting those and potentially causing damage. So I like to leave the furnace closed. The other thing is it actually air cools quicker with the furnace closed. With the way the path goes through the furnace, it'll cool down quicker. Okay, once we make all those choices, obviously we can click Next. And this gives us a review. So it tells us the instrument and what signals we're saving, etc., etc. So once we can flip through this and look at it and say, yeah, that's what we all wanted to do, and then we say Next again. Now it asks us for our sample information. So we can put our sample name here, and comments. We have a place here for comments that you can put in some information. Could be a lot number, it could be basically anything that you want to put about the sample. Data file name. This little icon right here is our browse icon. You click on that, you can go through the directory structure of where you want to store the file, and then type in the file name. Then we click on Next. Now it gives us our notes page. So we've got operator. You put in your initials or your name, and then pan type. In this case, I've got the alumina or ceramic pan. Then we've got a place here for extended text. This is like more notes. It's up to 500 characters, so you can write quite a bit of information in there. And lastly here is our purge gas settings. Now we're going to talk about this a little bit more, but right now this run is going to be in nitrogen at 100 mils per minute. And this flow rate is going to be controlled by the mass flow controller. And then we click on Next. Now it gives us our checklist. And it says, is the purge gas on and connected? Check. Have you carried the sample pan? If not, you need to. And then have you loaded the sample? If not, you need to do that. And then once you're ready, you can just hit Start to start the run. If you hit Finish, it'll take you back to experimental view, and then you can go in and start the run. But if we hit Start here, we're going to go and start running. Now this is our experimental view during a run. And a couple things to point out to you is right up here in our sequence, it shows a little green running man next to run 1. So if we have multiple runs in a sequence, whichever run is actually going would be highlighted, and then it would have the green man running beside that. Up here in the status line, it tells us that we're heating. Here's the temperature that's the current temperature, excuse me, and then here's a segment. So ramp 20 degrees a minute to 1500 degrees C. And if we look at our signals, you can see here's our temperature here, 31.12, which, lo and behold, matches that temperature there, kind of a good thing. Then we have our weight percent, etc. Sample purge gas flow rate, all that kind of good stuff, okay? Now down here in the real-time plot, this is showing our data as we're collecting it. Now this was just at the very start of the run, but you can see basically we're right here at 100%. We've got heat flow and weight percent that we can monitor versus temperature. Now remember I said that I showed you the real-time plot full screen. So if we click on this icon here, we'll go into, I'm sorry, let's go through this one first. Now, as we're running the sample, there's a couple things that we'll see. This is the experimental view. And here we've got our sequence, and we've got our little running man right there, a little green guy running. So it tells us that run number 1 is in progress. Here we've got that we're heating. Here's the current temperature. And here's our segment that we're in right now. Up here you can see that there's 74 minutes left in this run, the temperature again, and we can look at purge gas flow rate or weight or something like that. Down here we've got real-time plot. So it shows us that right now we're looking at weight in percent and heat flow in milliwatts. During the run, we can modify a method. And you do that by doing a right mouse click in this box here, and you come up with this box here that says modify running method or go to next segment. If we had multiple segments here, if we clicked on go to the next segment, it would go to the next one. In this case, it would go to the end of the run. If we click on modify running method, it takes us in here to our method editor, and we can go make changes. So say that we decide we really don't want to heat it all the way up to 1500, we can go in here and highlight that, change it now to 1200, and then click on Send Changes. Okay, now we've made our run. We're going to go in and use universal analysis to analyze the data. So the first thing we do is, we're back in our experimental view. Now notice here we've got the red check mark. What does that mean? That means that the run was completed successfully, which is always a good thing. Now this icon here is going to launch WinUA. If UA was already open, you could just click on it to bring it up on your screen, but in this case we're going to start it. When you first start it, you're going to get a blank screen, and typical Windows notation, we can use that box to open up a file. Now we're going to go through here and find the file and open it. We're going to look at this KLN file, and it brings up our basic information, and then I'm going to go in and look at signals. So I click on signals. Now what I normally look at for an SDT is heat flow on Y1, weight on Y2, sometimes I'll look at the derivative of weight on Y3, and then usually temperature on the x-axis. So these would be the signals that you would store and look at. Once we do that, then we get this file here. Now we can see that our green curve here is our DOC curve, our heat flow data. And then our blue curve is our weight percent data. And if we just look at this in general, we can look at weight percent here, and we can see that initially we see a small weight loss, and then we go up, and then we see a fairly larger step. During that larger step, we're seeing an endotherm. And that endotherm is going to be caused by that weight loss that's going on. As we go up to a higher temperature, we see this sharp exothermic peak here. But we don't see a weight loss associated with that. And that's really one of the main benefits of the SDT, is that we can see transitions like this that don't show up as a weight change. But one of the things I like to do with this is I like to reposition this so I have separation of the two graphs. And I do that by stacking the axis. So if we go to Rescale, Stack Axes, this is what we get. So we get our heat flow data up here and our weight loss down here. It's just a little bit easier to look at it. Now, we're going to do some analysis here, but before we do that, whatever the box is around here, around the Y1, that's the active axis. So now that's the axis that we're going to be analyzing. So if we go and look at these two peaks here, we've got this endothermic peak here during the weight loss, and we've got this exothermic crystallization peak that is not associated with the weight loss. So if we want to analyze this first endotherm, we're going to go into Analyze, Integrate Peak, and we're going to use the sigmoidal baseline because there's a shift in the baseline. Now, I'm not going to go through all the ins and outs of UA in this presentation. There is a UA QuickStart course, and there's also an advanced UA course that you can take to get more information on universal analysis and all the ins and outs. But we're going to use a couple key features here. So we're using the sigmoidal baseline. We're going to pick our points before and after the transition. Now you do that by using the left mouse button, dragging the cursors to bracket the peak of interest. So we're going to put one peak here, and then we're going to drag the other one cursor here, and we're going to drag the other cursor here, and we're going to do a right mouse click in free space. So that means someplace out here where there's not a curve. If you do a right mouse click on the curve, you get options for that curve. So you don't want to do that. Right mouse click in free space, and then we get this box. So we can say accept limits, and it does the analysis for us. And what we get here is, one is our peak temperature. So this 546.44, that's that peak maxima right there. Or in this case, a peak minima. And then this measurement up here is the peak area. So that's the area underneath the curve. So if we, from underneath this baseline down here, that's our peak area in joules per gram. So that's the heat of this decomposition reaction. And it's endothermic, right? So that's the heat that goes into that sample. Now the extrapolated onset temperature is 473.59. The extrapolated onset is a line drawn tangent to the curve at the inflection point and extrapolated back to the baseline. So it's this line here and extrapolates back to the baseline there, and that temperature is 473.59. So that's the measurement of that. Now we can repeat this for this exothermic peak, and in this case we see the extrapolated onset temperature here, we see the peak maxima there, and we see the heat of crystallization here. And this is exothermic, so that's heat given off by the sample. Now if we want to analyze the weight change that's occurring here, we need to either click on this curve or click up here on Y2 until we get the box around it. We need to make that the active axis. So now that we've got that box around there, the weight curve is active, and we can go in and do analysis. If we go into Analyze Weight Change, we're going to get two cursors again. Use the left mouse button. Now what we're going to do, because we're going to analyze this little small weight loss here, and then we're going to analyze this bigger one. But I'm going to take that very first data point. So I'm going to take the cursor all the way off the curve. See, someplace back here off the curve, and I'm going to release the mouse button. What this does is it picks that very first data point. Then I'm going to take this cursor, and I'm going to drag it and put it somewhere up in here. Position the second data point, right click in free space again, and accept it. Now that gives us our weight change in percent and milligrams. So you can see it's 0.1452 milligrams. That's a little over 0.6%. That's the weight loss that we saw there. Now if we want to see this larger weight loss that occurs here during the decomposition, we would go back into Analyze Weight Change. Now we're going to get our cursors, and they're going to start off at the same point we did the measurement last time. So what we want to do is we want to take this cursor, which is the first one here, and we're going to leapfrog it over this one. So we're going to take it from there and then drag it over to here. Okay. Now the second cursor from that first weight loss is now going to be our first point for the second weight loss. We're going to leave that in the same place. So now we're going to do our right click in free space and accept it, and we see our weight loss there of a little over 13%, or about 2.9 milligrams. Now once we get the analysis done like we want to, and we can grab the labels and drag them around and annotate and all that other stuff that Peter will teach you in the Universal Analysis course, then we can go in and do a print preview. So File, Print Preview. This will tell us how it's going to look when we send it to the printer, or if we export the plot to a Word document or something like that. Okay. And once we're satisfied with that, we can go File and Print and send it to our printer. And print it, whether it be a printer that's hooked to our computer or a network printer, etc. Okay, now we've gone through introduction and how to run a typical sample. Let's go through some of these other topics. Here's the other topics that we're going to cover. We're going to cover calibration, We're going to talk about running experiments using templates instead of using the wizard. We're also going to talk about using custom procedures and saving custom procedures. Then we're going to talk about some purge gas considerations, sample preparation, some maintenance issues, and then help. Now when we get to help, we're going to talk about the help that's built into the software, plus also give you some general numbers that you can call at QA Instruments to get further help. Let's talk about calibration to begin with. Now there are 4 basic calibrations on the Q600. The calibrations are all performed in the calibration mode. The calibrations are done in this order that's listed here. Now, depending exactly what you're wanting to do with the SDT, you may not have to do all of these calibrations. In fact, typically, the second one here is not done. But we have TGA weight calibration. This second one is a DTA baseline calibration. It's not required when using this as a DSC. So that's why we normally don't do it, because we normally use this as a DSC. Then there's a temperature calibration, and then there's DSC heat flow calibration. And that's not required if you're only going to use it as a DTA. But generally you wouldn't want to do that. The TGA weight calibration. This consists of 2 runs. The first run are empty beams. So just like we've got here. No pans, no nothing, stick them in the furnace, run it. The second run is the 2 calibration weights that come in your accessory kit. Now there's a sample and a reference one. They go on the corresponding beams. Here's the weights for the sample side, the weights for the reference. How do you know which one is which? It's kind of hard to see here, but on this right here, there is an S on one of these. Now these weights basically look like a ceramic pan that's filled in all the way. That's sort of what they are. And so the one with the S is the sample one, and then the reference one. So you make these runs just using the software like we showed you earlier, and then you would go in and analyze it. Now to analyze, if we're back in our experimental view, this icon here is our calibration analysis. So we click on that, and it asks us which calibration do we want to do. So this is a weight calibration. So we're going to click on weight. When we do that, it asks for our sample files. So we use the little browse buttons to load our calibration files. Without weights, empty beams, and with weights. Once we do that, it plots out this data here. So this is uncalibrated sample weight in millivolts. Okay, don't get worried about what that sample or what the units are there. But if you do a right mouse click in free space, then you're going to get this pop up. So you can go to Analyze, and it's going to give you 2 cursors. Now normally we recommend leaving it where it is, which is 200 and 1400. So if you do that, and do another right mouse click in the free space, and say Limits OK, then that's our analysis. And you can see that here's a flat line here that we're trying to adjust for any growth of those beams that could have changed the weight because of the moment arm there. Now if we do a right click in free space, we can accept those results. And once we do that, it sends it to the instrument, so we don't have to worry about it. All right, it's done. Now, DTA baseline calibration. As I said before, it is not, NOT, not required when using this as a DSC. What does that mean? That means when you're saving the heat flow. It's just one run, and typically the easy thing about it is if you're going to do this, we use the first run from the weight calibration. And the DTA baseline is corrected for slope and offset, which results in shifting and rotating that baseline. So we make that run, we go into calibration, say DTA baseline, we get our file here, we do the right mouse click to get our analyze, and we get the cursors. If you're going to do this, you want to pick here after this startup transition here, and in this case, in this instrument, we saw that it tailed off at the end of it. So you'd want to generally pick it someplace here on the flat part here and here. Do a right mouse click and say OK, and you see it's going to shift that out and make it flat. Now what you'll see happen is that with the DTA and its DTA mode, you don't get as good a baseline as you get with the DSC mode. And that's one of the reasons for going ahead and doing that calibration and running it in the DSC mode. And then we do our right mouse click in free space, go into Analyze, and accept results. Now, temperature calibration. You want to use high purity metal standards for temperature calibration. Zinc is included in the accessory kit, and that zinc melts at 419. But there are other standards that you could use, like tin, aluminum, silver, gold, and nickel. Nickel is right up there at the end of it, but this instrument will look 1500. But all these others are well within the range of what the instrument will cover. So once you make that run, you would go into the calibrate analysis and do temperature. We do that, we're going to pick our zinc sample here, and it's asking what standard. We're going to say zinc, and here's the melt point. We're going to say OK. Now this graph looks a little funny here, and the reason is, here's the method log that I used for this sample. And what we did is we equilibrated at 470, sat there for about a minute, equilibrated at 325, sat there for a minute, and then started ramping. Why did we do this? We did this to pre-melt the zinc. So we heated up to a high temperature above the melt, let it sit there to let everything melt, then we cooled it down. As we're cooling it down, we're actually seeing the crystallization of the zinc. And then we start heating up, and this is what we want to analyze. This is our melt. Now we do it the first time because when you put, whether it be a powder or some zinc, a piece of zinc or whatever, you want it to melt at once so it flows and gets a little better contact with the bottom of the pan. And that's why we're doing this. So you do the right mouse click for analyze, you move your cursors before and after the peak, do a right mouse click, say limits OK, and then there's our temperature calibration. We do the right mouse click, we go into Analyze, Accept Results, and it sends it to the instrument. Now there's one other calibration, and that's the DSC heat flow calibration. This consists of two runs, empty pans, and then a sapphire standard. And notice I said empty pans here, not empty beans. Okay? The measured heat capacity of the sapphire is compared to the literature value at multiple temperatures, and then it's fitted to generate a heat flow calibration curve, or what we call an E-curve. Now to make those runs, you put the pans in there, tare it, run the pans, then you put your sapphire in the sample pan, run it. Both those done the exact same way, same temperature range, same heating rate, and then you would go into the calibration analysis again and do DSC heat flow. We've got our little browse button again, one for the baseline, empty pans, one for the sapphire, say OK, and then this is what it looks like. So we're going to do a right mouse click, go into Analyze, and we're going to pick a point here somewhere on the flat part of the curve generally. In this case I picked about 300 to about 1400, did a right mouse click, says OK, and there it goes, we calculate the E-curve. And the E-curve is plotted here in red. That's the calibration that's done and fitted to the sapphire of what we actually measured versus the theoretical. Okay? And we can do a right mouse click, Analyze, Accept Results, and sends it to the instrument. So that's it for calibration. The next thing we're going to do is go and talk about running experiments using experimental templates. If we're back on our experimental page and we go to Test, we've got these templates. So you can see we've got Custom, Ramp, Isothermal. We're going to pick Ramp, but this is where you would select that. Once you do that, you finish filling out this page. So we put in our sample name, any comments, click on this icon to get into our file structure and decide which folder we want to save it in and give it a file name. Once we do that, we click on the Procedure tab. To get the Procedure tab, it's going to give us just what we saw earlier about start temperature, final temperature, heating rate, the switch gas, and the hold time, advance and post test, just like we saw earlier. Once we get satisfied with that page, we click on the Notes page. And this, same as we saw earlier, gives us our initials or name, which pan we're using, extended text, and our mass flow controller settings. Once we do that and we hit apply to apply all of our changes, then we can start the run by using our little start icon here. Simple as that. Now, custom procedures. In the custom procedure, we want to use the custom template. So if we go here to test and pick the custom, and then we go to procedure. We go to procedure, we see it looks a little bit different. We now got this box here for editor. If we click on editor, this gives us our method editor. Now I've got a blank page here, and so I'm going to show you how to create a method. So if we were to start off with an equilibrate, we'd go over here to equilibrate, do a left mouse click, hold it down, and drag it into our method. So that's what we're doing here. We clicked on that, and we drug it over here. This is what we see when we're dragging it. And then we'd let it go, and it pops it in there, equilibrate. And we can go in and type what temperature we want to equilibrate at. Maybe next we want to do a ramp, so we would follow that, go over and click on ramp, and then drag it over. And then maybe an isotherm, we would do that. So once we go through and create everything that we want in the method, we can close out of the editor. And then now we've got a choice here to save the current settings to a procedure file. So if we click on that to save it, it's going to give us a point where we can browse and find what folder and the file name. But this is what we're saving. We're saving the mode that we're in, the signals that we saved, the method that we saved, our advanced parameters, and our post-test conditions that's down off this page. We're saving all that. We're not just saving the method. And that's really what a procedure is. It's the method plus a lot more. Now once we save a procedure, if we want to open up a previously saved procedure, we choose custom and then go over here to this open icon. And we click on that and we can sit here and open up this test procedure. And we've got that open now. And you can see it says custom, and then it goes through the path to find that custom procedure. Now this icon here is what we can use to view this procedure. So we can see it tells us all the particulars about the procedure, including the method, and we can print from there. So this is a way that you could print out your procedure. This is the way to do that. Okay, we've gone through using templates and using custom procedures. Now let's talk about purge gas considerations. Now there's two purge ports on an SDT. The primary purge port and the secondary. We're going to talk about secondary here in a minute, but let's talk about the primary first. The primary comes through the ports on the back of the instrument. Now here when we say gas 1 and gas 2, both of these are for the primary purge. The flow rate is controlled by the built-in internal mass flow controller, and that includes a gas switching accessory, so if you want to switch from gas 1 to gas 2 during the run. Now if you go into the experimental view and say Tools and Experimental Preferences, we'll get this box here. And if we go here to the MFC purge, this tells us that gas 1 is nitrogen and gas 2 is air. We use these drop downs to select which gases we've got plugged into the back of those ports that we showed. So now I would need gas 1 plumbed up to nitrogen and gas 2 plumbed up to air. Now if we go to our notes page, this is where we select which gas we're going to make the run in and what flow rate. So here we're going to run in nitrogen, and the flow rate we've got set is 100 mils per minute. Now notice this, for those that have a regular DSC, notice this is twice what the flow rate is typically for a DSC. But that is normal. The range that you can put in here is from 20 to 1,000 mils per minute, and the 100 mils per minute is typical. Now the primary purge gas goes through the balance chamber, and I'm going to show you a picture of that in a second. So you only want to use these recommended gases, and these recommended gases come from the manual. So I didn't make these up, these come from the manual. But those gases are nitrogen, helium, argon, air, and oxygen. Now normally on an SDT, I'll run it either nitrogen or argon unless I'm trying to get something specific that I'm looking for oxidative results, and then I'll run in either air or oxygen. I usually do not run an SDT in helium, and that is because helium is so thermoconductive that when you get up into the high temperature ranges, like up above 1,000 degrees, it really makes that furnace have to work to get the instrument up there. And I found that I don't think you get as good a results as that. Now here is a picture of the balance. And right here that I've got circled, that little fitting that you can see down there, and there's a hole there, that's where the primary purge comes into the balance assembly. And it purges this whole thing. There's obviously a lid on this, but it purges this whole chamber and comes out right through here where the beams go through that hole that the beams go through. So it's got to purge this whole chamber where we've got our balance mechanism, we've got our wires that come here off the thermocouples and beams, we've got wiring. So this is a big area. If you get air or oxygen in here, it takes a while to purge this out. So that's kind of a clue. If you're running samples where maybe you're running in nitrogen, and then you want to turn around and run a sample in air, if you put air through this balance chamber, and then you're going to run back and run a sensitive sample that would be, or a sample that would be sensitive to oxygen or air, it would take a long time to purge out all that out of this chamber. So you may not want to do that through the primary purge. You may want to do that through the secondary purge. Now the secondary purge enters through a port on the back of the balance housing. And I'll show you a picture of that here so you know what I'm talking about. Now this flow rate does not go through a mass flow controller. It's controlled by an optional external rotometer or flow meter. And you can get that from us, or you can get it from Brooks or other people that sell flow meters. The typical flow rate for the secondary purge is a lot lower. It's 20 mils per minute. You always want to keep the secondary purge lower than the primary. That way the balance is always kept in that inert gas. Now the secondary purge comes in, this is the fitting here. So this is a cap, but if you took that cap off, that's where you would plug in your purge gas. Now that comes in here, and you can see this tube, this vent, but then right here is where it goes through the wall into the instrument. And then that tube goes down underneath the balance housing and around, and it comes up right here. So you can see that little right there in between those beams. That is the tubing for the secondary purge. So it comes out and sticks out a little bit in between the beams, and it is made to introduce a purge gas that would go in and react with the samples. But it's not going to go inside this balance assembly. So you could use oxygen or air with that and not have to worry about contaminating your balance. You could also use carbon monoxide or carbon dioxide with that secondary purge too. Once again, these recommended purge gases are from the manual. Now there's a couple other recommended gases I didn't list here, and that's nitrogen, helium, and argon. But normally you probably wouldn't do that through the secondary purge. Now let's talk about sample preparation. As with any TGA experiment, you want to maximize the surface area of the sample to improve weight loss resolution and temperature reproducibility. What does that mean is that powders are best. The sample weights that we usually use for SDT is 10 to 20 milligrams for most applications, but you might want to increase that if you're looking at very small volatiles. Other tips is you might want to use brass tweezers to eliminate static effects. You want to make sure you tear a clean sample pan before every run. And then you want to distribute the sample evenly over the bottom of the pan. Now here's our different sample pans. It shows a picture here. The alumina or ceramic pans are the ones that we use most often. They're good for corrosives and inorganics. They're available in 40 and 90 microliter sizes. And the 90 microliter is what we recommend for DSC work. That's what we found the best results are. Platinum pans are useful for most materials. They're non-porous, which is a plus, but they do tend to alloy with most metals. And they're available in 40 and 100 microliter sizes. Maintenance issues, cleaning the furnace. if you're running all your samples in something like nitrogen or argon, an inert atmosphere, every 10 to 20 runs, you should heat up to about 1,000 degrees in air to clean the furnace. Then you can hook that up to the secondary furnace where you didn't get the air in your balance. Now, to maintain the beams, it's very important that when you load samples, you don't do it while it's sitting on the beam, because if you spill any around, it could go and get stuck there around the edge of the pan where the pan sticks to the beam. You could actually have a sample where it welds the sample pan to the beam, and you would have to go through and replace the beams. Not a good thing. If the beams get discolored, run up to about 1,000 degrees in air, like we talked about for cleaning the furnace, and that would typically clean the beams off. Let's go in some help. Now, these first thing in help, we're going to be talking about the help that you can get in the software, and instrument error messages, and logs, etc. And then we're going to have a slide or two where we talk about some phone numbers that you can call to get help as you're running samples. Now, if you are in the process of doing anything to the SDT and you do something wrong or the instrument has an error, it'll pop up this message. So in this case, it says instrument error message for the Q600 that the sample purge gas cannot reach specified flow rate. And then here's the error number here. It's error number 656. Okay, so normally if this happens, we're going to click on OK. It's going to clear off the screen, and then we're going to go and check our cylinder or whatever to make sure that we got gas. But if we click on OK, and then we come back a few minutes later and say, what was that error again? What we can do is go to the instrument log, and that's this icon here. If we click on that, it shows us a log of all the errors, plus other information like when we started a run, when we completed and saved a run, etc. If we highlight this error number 1 here, which is our sample purge gas cannot reach specified flow, if we highlight it and click on error help, we're going to go in and see this. Okay? So this tells us that message, 656, sample purge gas cannot reach the specified flow rate. It tells us the problem and a solution. Now, if you're working on a particular page, like in this case the summary page, and you want help for that specific page, you just click help here that's on the bottom of the page. And that brings up using the summary page. So we could sit here and read, and it tells us different things along here. If we want to go into select signals to store, we could click on that blue. Anything that's blue is a link, and it would bring us up here. And you can see there's another link there. So this is the help that's built into it. Now this is online help. This is put into the software. When you load it on your instrument, it's there in your computer. Now there's also a manual. The Getting Started guide is also online. So if we go under Help, Getting Started, this brings up this manual. We can go through, and in this case I've got under Chapter 2, Installation and Secondary Purge Line. Here's the information in the help for the secondary purge. And if we go to the next page or so, I don't have it on here, but this is where it would tell you which purge gases you could use. But here it shows the secondary purge fitting, there's the instrument cabinet, there's the housing over the balance, etc. Okay, further help. We have a lot of online courses, as you may have seen. If you haven't seen, you should really look at our website and see what we've got offered. We've got QuickStart courses. That's like this course, which teaches you how to get started on running your instrumentation. And then we've also got some advanced courses. And we're working on more advanced courses, and those are available too. So look on our online page and see the different courses that might be beneficial to you. Every other month or so, we give a applications and theory course here in Delaware. Now this is a lecture-based course. It's not hands-on, but it's a day for each technique. Now SDT is kind of an in-between because it's a DSC and a TGA. So if you have an SDT, we cover part of that in the DSC course and part of that in the TGA course. Now when you buy an instrument from us, you get tuition for one person to this course at no charge. But if you haven't bought an instrument from us recently, or if you have more than one person that wants to attend that, these courses are available for $400 per person per day. Now for on-site training, you can have a TA Instruments application specialist come to your lab and give you training on your instruments. Now this can be configured any way you want it. It could be all day of a lecture, sitting in a classroom. I've done that for like 35 or 40 people. It could be part lecture and part hands-on, or it could be just all day hands-on. I've done any of those combinations. It really depends on what the customer wants. When we do the hands-on, we do it on your instrument and we run your samples. So that's probably the best way for you to learn. Now there is a charge for this. It's $1,500 a day plus expenses. But that'll get one of us from applications into your lab, and we will sit there and spend the time with you running your instruments. I've gone in and spent a day per technique with people, or I've spent 2 days on one technique. Once again, we can configure it per year. And on the expenses, don't worry, we don't fly first class or anything. It's just regular coach class to get there. Now stay tuned to our website for further training opportunities. And here's our website address here, just tainst.com. And there's a support, and if you go into support, there's training. It shows a lot of the different training things that we're doing, the online courses, on-site training, etc. Now, other things that you can do for help. If you're in the middle of doing something and you have problems, you can call our applications hotline. So here's the number here and the hours, Monday through Friday, 8 to 4:30 Eastern Time. If you call that number and it goes to voicemail, that generally means that that person's on the line with someone else. So leave a message and he'll call you back. If we get calls, calls we get today, we answer today. You can also send an email to AnswerMan, and this is available from our website, or you can just direct at answerman@tainst.com. There's also a service hotline, and here's the phone number and the times for that. Now, sometimes I realize that you've got a problem with your instrument or a problem running a sample, and you may not know whether it's a service-related problem or an applications-related problem. Please call one of us, okay, and we'll direct you to the right person, but we'd love to have you call, and either we help you or we pass you on to service or vice versa, than to have you be frustrated and not get the data that you need out of it. And then your sales and service representatives are also good sources of information. Well, that's about it. Thanks for attending. Join us for other of our e-training courses. Don't forget our website for more information. Now remember, back when we started this about an hour or so ago, I said if you have specific questions, email us. Here's the address, webex2@tainst.com. Tell us the slide number, and tell us what presentation, because we have a lot of these presentations. So tell us it's an SDT QuickStart and slide number whatever that you have questions on. Maybe like 155 in this case. And then lastly, here's our picture of our building. Thanks a lot. Appreciate you joining us, and take care.